is coming up. Normally you want to do these sooner, that way you can review it at least once or twice or more. The sooner you review it, the better. But anyway, I'll just go through it. If you want. We'll just do this so we have more time to review it. All right, so this problem is 128 is based on active example 3-29. This is active example 3-29 in the little pop-up window here. Suppose that you've just landed a part-time job that pays $9.25 an hour. You'll work 5 shifts each week, and the shifts are 4 hours long. So we can get some conversion factors for that. So the first conversion factor is we get $9.25 per hour. The second conversion shift is we work 5 shifts per week. So 5 shifts per week. And the third conversion factor is the shifts are 4 hours long, so 4 hours per shift. And of course we can flip these over. So I just draw it this way, but if we need to, we'll flip them over. And so we'll have a set of 6 conversion factors here that we generate from the first two sentences. You plan to save all of your earnings to pay cash for a 50-inch 1080p Smart Plasma HD TV that costs $1082.49. So this is old, obviously, because $9.25 is long gone, and then plasmas are no longer around, and the prices are pretty high. So $1082.49, tax included. And so the TV cost $1082.49. This could be another. I don't think he's going to buy more than, or she's going to buy more than one TV. So it's per TV. And the question is, you're paid weekly. So at the end of each week, you get to check how many weeks must you work in order to save enough money to buy the television. You might also be interested in knowing how much cash you'll have left for video games or other goodies. All right, so what normally we do when we have a dimensional analysis problem is we look first for anything that's fixed, that you can't change. In other words, not necessarily the ratio. Ratio is not fixed. This is a ratio. If you work 2 hours, then it'd be double. 3 hours would be triple. This is the same thing. However, this is kind of fixed, $1082.49, because I'm not going to buy more than one TV. And so normally we start off with $1082.49. That's a fixed number. That's where we start for dimensional analysis. That's dollars. And then what do we do? Well, I don't know. What we do is we just try to figure out how can we eliminate dollars and replace it with something else. Is there something that relates dollars to something else? Yeah. So you look here, and there is this one. But we need to flip it over. That's not a big deal. We can flip it over. So that's going to be $9.25 per hour. And so we get rid of dollars and replace it with hours. And so that's how many hours this person has to work, but they aren't going to work it continuously. They're going to work it in terms of shifts, in terms of whatever. And so here, we need something that gets rid of hours. Do we have something that gets rid of hours? Yeah, we can go from hours to minutes. Would that be helpful? No. Hours to seconds?
No.
No, that would be going wrong. But here, I see I have hours to shifts, so let's do that. 4 hours per shift. And so the hours canceled, that tells me how many shifts I need to work. Well, I don't want to know how many shifts, I want to know how many weeks I have to work for this. And so here, I got to get rid of shifts. Is there something that gets rid of shifts? Yeah, right here. Now, there's 5 shifts per week. And this is going to tell me how many weeks I need to work for the TV. So let's see how many weeks it comes out to. And so that's 1082.49 divided by 9.25 divided by 4 divided by 5. 5.85 weeks. Well, they're not paid in the middle of the week. They're paid at the end of the week. And so we have to say 6 weeks. Because if they work 5 weeks, it's obviously not enough. They're going to need 6 weeks. And they're going to have some money left over. Do you know how much money is going to be left over? Well, they're going to have 0.15. You know, they didn't have to work that extra 0.15. And if they were paid continuously, then they could stop here, right? But since they had to work the extra 0.15 weeks, you know, we can figure out how much extra spending money that is. And so extra 0.5 weeks work was not required. And so what we'll do is we'll just figure out how many dollars that translates to, because we need to get rid of weeks. How can we get rid of weeks? Well, we can convert it to shifts. In other words, we're working backwards. And then shifts, we need to get rid of shifts and convert that to hours. And then from hours, we'll convert it back to dollars. That's $9.25 per hour. And so shifts cancel, weeks cancel, hours cancel, that leaves us with dollars. And so we could do that here. It's going to be 0.15 times 5 times 4 times 9.25. $27.75 of extra money. Is that okay? However, when you earn $9.25 per hour, you don't take home that much. And so here, you calculated, in that example, you calculated that you would have to work 6 weeks to earn enough money to buy a 1082.49 television. You'd be working 5 shifts of 4 hours at $9.25, but alas, when you received your first paycheck, you found that exactly 23% of your earnings had been withheld for Social Security, federal, and state income taxes, and workers' comp insurance. Taking these into account, how many weeks will it take to earn? Well, it's going to take longer now because 23% of your money is being withheld. And so this is the difference between advanced and standard problem. An advanced problem doesn't require the labeling that, well, actually, I got it backwards. A standard problem does not require the labeling an advanced problem requires. Advanced problems, we have to be very detailed in how we label things. We have to be very detailed because this is not labeled enough. And so let's take a look first at the 23% here. 23% withheld. Oops. Turn this off. "23% withheld" means this. A percentage is what? What do you call a percentage? Parts per 100. So it's 23 parts per 100 parts. Parts of what? Income. And so what that means is that for every $100 of income, $23 will be withheld. And so we need to label that. And so this might be what we say is gross income. And And then $23, we'll just call it as tax. It's a tax. And so do you see, we can't label this $23 over $100 because that's not detailed enough. We have to list what the dollars are. In this case, it's $23 of tax for every $100 of income. So if every $100 is taxed $23, then how much do you have left over? How much after tax? Yeah, $77. And so what we say is if it's 23% withheld, then it's 77% net or take home income. You know. And so this is what you'll get. And so here what we can just do is we can just say that here, $77 of net income for every $100 of gross income. In other words, for every $100 you get paid, you're only going to take home 77 of those. 23 are going to be taxed. Does that make sense for this? And so now what we have to do is we have to do this. These dollars, the question is that net or is that gross? In other words, net is take home and gross is the total. And so when you look at the paycheck stub, you'll see the gross, but you know the gross and the net don't match. And so to buy the TV, can you buy the TV using the total dollars, or do you have to buy the TV using the net? Yeah, you have to buy it using the net because you can't pay it with the taxes. The taxes are gone. And so the answer is net. And so what we'll do is we'll add a net to this. This is the difference between advanced and regular here. And so we need something that cancels out net dollars, or we need something that cancels out dollars. Is there something that cancels out net dollars? Yeah. Okay, it's not this one, not the 23, it's actually this one. So we had to figure that out. And so what it is it's this. For every $77 you net, you're going to have to work $100 worth. And so for every $100 work. And so in other words, that TV is going to be more expensive, you know, or seems to be more expensive because of this. And so we'll need $100 gross income for every $77 of spending income. And so in this case, the net dollars cancel, and we're left with gross dollars. And so that TV is going to cost us, you know, because we have to pay two. You know, you got to pay the seller of the TV, and then you have to pay the government. So some people say, you know, some people calculate this. For every year, how many weeks of work do you have to do to pay the government? Have you heard that? And so there's some kind of index. And that index has been growing. Well, to buy a 1082 49 TV, okay, then times 100 divided by 77. That's going to cost you $1,405.83 in earned income. And so you're paying the government, well, $1,405.83 minus 1082, 49, you're paying the government $323.34, and then the seller of the TV $1,082.49. But it's not just paying paying the government. It's also for Social Security. So hopefully you'll see some of that money back, but I'm not sure. And then federal and state taxes to support the services, firefighting, But anyway, you're going to have to work more because it's not just paying the seller. You got to pay that. So $1,400. Well, how long is it going to take to earn $1,400? So what we need to do is we need to go from gross dollars or dollars. In this case, we're just going to go from dollars because there's no gross. Actually, we are going to go gross dollars because $9.25 per hour. $9.25 per hour. Does that take into account the tax? No. So this is $9.25 gross. You aren't going to see that per hour because some of it's going to be taken out as tax. And so the gross dollars cancel out the gross dollars and leaves you with hours. And then from the hours, we know that there's 4 hours per shift. So that tells us how many shifts we'll have to work. And then there are how many shifts per week? 5 shifts per week. So let's see, it was 6 weeks, but now you're going to have to work extra, right? And so how many weeks extra do you have to work? So 1082.49 divided, or times 100, divided by 77, divided by 9.25, divided by 4, divided by 5. 7.59 weeks. They want this to the nearest week, so 8 weeks. So in other words, you're going to have to work 6 weeks for the TV and an additional 2 weeks for taxes. So a total of 8 weeks. Does that make sense? So, and most of the problems you don't have to label things as detailed in Chem 4. Except for this, like this advanced problem here, or some of the more challenging problems in Chem 1. Okay, other questions? No other questions? All right, so the plan is to finish up Chapter 5 and take a look at Chapter 5 homework, and then take a look at the test. One of the questions that came up is an answer key posted for that sample test. And the answer is no, there's no answer key for the sample test. The reason I don't post an answer key for the sample test is because in science you have to learn how to check your own answers, or check your own answers as best as you can, because there are usually no answer keys in science. Like when you go on, and it happens sooner than you might think, but when you go on, like when I was a student, there was always somebody I could ask, what's the correct answer? Am I doing this right? That kind of thing. But pretty soon you'll hit this point where, is that the right answer? There's nobody to ask. There's nobody to ask because who's going to pay you to do something that somebody's already done? If somebody already has the answer to it, then why pay somebody to do it? I mean, they already know the answer, right? And so in science, it works that way. If you want to work in science, you're going to have to do stuff that nobody's done before. Well, if nobody's done it before, then there's no answer key. If there's no answer key, then how do you check your answer? And so, well, we got to think about that because it's an important question. How do you check your answer? Well, one way of checking the answer is just, seeing, did you go through and set up everything properly? Did you double check your calculation? These kinds of things. Going through and seeing if everything's set up properly, do the units cancel? And so you should go through that sample test, and hopefully you'll understand the problems and the calculations to the point where you can say, okay, I set this up correctly, everything looks good, I should have the right answer. If you feel shaky on it, like, I really don't know, I don't know if that's right or wrong, then what you should do is go back into the book and then read that section and then do more sample problems in that section until you feel more confident in that. Because what you want is a certain level of confidence in your understanding to be able to do this. But, this is the first test, so if you have questions, I'm not going to pose an answer to you, but you can always ask me. I'll tell you, if it's right or wrong. Okay, where did we leave off last time? Here? All right, Dalton's theory, this was in the 1700s, so things have changed since then. One thing that's changed is the development of nuclear chemistry and this indivisible nature of atoms. Atoms can either be created or destroyed. It's actually not exactly correct. In nuclear chemistry, some atoms decay into other atoms. And some atoms are made from smaller atoms, bigger atoms might be made from smaller atoms. And so, atoms have subatomic particles. Okay. Then this one, all atoms of an element are identical. That's not exactly correct because there are isotopes. Do we talk about the atomic mass unit? How are atoms weighed? How do you weigh atoms? Do you know how atoms are weighed? Can you weigh an individual atom on a balance? No. Small. You have to weigh them using what? What was the thing that they used to weigh electrons? What that was called? We talked about weighing the electron, I think, yesterday, so. Look back. The mass spectrometer. And how does it work? Roughly, you don't have to be.
The deflection from the carbon flow.
Shoot beams of electrons. So yeah, that's correct. You shoot beams of electrons. Mass spectrometer is probably. Did I show the homemade? Remember the homemade? What was that? CRT. The homemade CRT. That's very similar to mass spectrometer, but mass spectrometer obviously is a lot more. Of a professional instrument, but you shoot beams of electrons, and those beams of electrons are what? How can you figure out their mass? The beams of electrons, there's no carbon-12 in there for the mass of electron.
Based on how much it deflects, you can see if it deflects more, it must be lighter than so much.
Yeah, right. Based on how it deflects. And so lighter ones are more deflected, heavier ones are less deflected. And then we could do that. We could see that in what's called mass spectrum. This is an example of a mass spectrum. And so here are some lighter atoms. It just happens that there are a lot more lighter atoms. that the height of the peak just means how many atoms hit here. So this is a sample of neon gas. Sample of neon gas, most of the atoms hit here, but there are a couple of heavier atoms. There's one around 21U and one around 22U. This is around 20U. And they hit there. The lighter ones are going to be more deflected, so boom, they'll hit here. And the heavier ones are less deflected. They'll hit up here based on the magnet. I talked about carbon-12. What was the deal with carbon-12? So summarize the whole spiel about carbon-12. What's important about carbon-12?
They know that by definition it's exactly 12 atomic mass units, right? So they use that as like a reference to weigh other atoms.
Yeah, that's good. Is carbon-12 locked up in a vault in France? Why not?
Because it's so abundant.
It's so abundant. Which is better, you know, because if it's easily accessible to everyone, then anyone can calibrate their mass spectrometer without having to fly to France. Something like that. But if you wanted to properly calibrate your balance, then you probably want to fly to France and use the real kilogram, you know, the exact kilogram to make sure. And so, but anyway, carbon-12 weighs exactly 12U. There's heavier isotopes. If carbon-12 strikes there, then carbon-13 strikes a little farther away because it's heavier, has more inertia. It's harder to deflect. And then based on where it lands, we can use a little bit of physics to determine its mass. And this is the mass of the carbon-13, a little bit heavier, just about 1U heavier, but not exactly 1U. It's 13.0033548378. How many decimal places is that? It's 2, 4, 6, 8, 10 decimal places. What do we call that? Do we call that a highly accurate mass spectrometer, or would we call that highly precise? That's highly precise. For accuracy, we need to calibrate it. So we'd have to first calibrate it with carbon-12, and if we calibrated it, then it should be both accurate and precise. If we didn't properly calibrate it, then we don't know its accuracy, but it's very precise. Very precise means it can detect very, very tiny differences in mass. Extremely tiny differences in mass are detected with this. Versus if something's not very precise, if this was like 2 sig-figs, it's 12 or 13, can you really detect very, very tiny, minute differences in mass? No. And so we need this extremely high precision to determine or to detect very minute differences in mass. And so that's huge. Did I talk about oxygen 16? Did I talk about oxygen 16? Yeah, well, actually, take a look in your notes and see if you have anything about oxygen 16. Was there anything in your notes for oxygen 16? What was it? No?
8
Nothing?
protons and 8 neutrons.
8 protons, 8 neutrons. Anything else? Okay. This is called an arbitrary standard. Arbitrary. It's arbitrary, like Celsius is called an arbitrary temperature scale because somebody just arbitrarily picked the freezing point of water as 0. Whereas Kelvin is not arbitrary. Kelvin is what we call absolute. Absolute. It turns out in the 1950s, do you know it wasn't carbon-12? It was oxygen 16. Why oxygen 16? Because oxygen 16 is free and it's relatively abundant. But the problem with oxygen 16 is it's in air, and so air, is not as dense. There are other factors there, and so it was switched. Did I talk about this or not? I did talk about this? Okay, so that means what? Well, I forgot which one. I know I talked about it in one class, but I didn't talk about it in the other, so I guess I didn't talk about it in the morning class, so let's skip it now. And so that just means it's like a kilogram. If somebody got a different chunk of metal, let's say they lost that chunk of metal in France, what are you going to do? Well, better define a new chunk of metal as being exactly 1 kilogram. And if the new chunk of metal weighs differently than the old chunk, then everything has to be reset to the new arbitrary standard. And so when we look at old tables, we've got to be careful with that. But anyway, that's oxygen 16. So if you look at the old ones, it used to be that oxygen 16 is exactly 16, and carbon-12 would not be exactly 12. Carbon-12 would be close to 12. It would be something slightly off. But is that okay to do, or is there something not right about it? It's fine to do because somebody can come up with other units as well. Somebody can come up with the other temperature scale. Let's say I don't like it. The Celsius steps are too big. The Fahrenheit steps are still too big. I want an even finer, even more precise thermometer. So I'm going to go with a new. So you can do that type of stuff. It's fine. And so anyway, once we have this, then we can weigh everything else. And so we calibrate our mass spectrometer, and then we start weighing these. But wouldn't it be great if you could just predict it? Using theory. Can you predict this using theory? In fact, can you predict how many isotopes there are for hydrogen? How many isotopes are there for hydrogen? 2. When you look at the periodic table, is there anything that tells you that there are 2 isotopes? No, there's nothing. And so how did you know there are 2? Because somebody must have taken observations and observed there are only 2 isotopes for hydrogen. And so what the physicists are trying to do is they're trying to come up with a theory such that they can predict these things. Predict how many isotopes and what their relative percentages are. But when we go down here, it looks like there are 2 isotopes here. But when we get to oxygen, how many isotopes are there? 3. If you look at beryllium, there's only 1. But we don't really worry too much about beryllium because it's so toxic that nobody uses it. And so what we're going to do is we're going to look now at water and look at how we can make water. So water is made up of 2 hydrogens and 1 oxygen. And I'm going to link them together with a line here. This line just shows that they're attached or bonded together as one unit. And this unit we call a molecule of water. But when we look at a molecule of water, are all the water molecules the same? You had some water today. Were all the water molecules the same? No, they aren't the same because we have some choices about this. So for example, there are two types of hydrogen. One is hydrogen 1, the other is hydrogen 2. So we can make it a water like this, hydrogen 1, but there are three types of oxygen. What are the three types of oxygen? There's oxygen 16, 17, and 18. And so what I'm going to do is I'm going to pick 16 for now. So I'm going to build a water molecule that consists of one hydrogen 1, one oxygen 16, and one hydrogen 1. That's H1, row 16, H1. And then I might be interested in how much this weighs. You know, how much does this weigh? Well, if I look at the mass number, you know, the mass number is 1, 16, 1. So if I look at the total mass number is 1 plus 16 plus 1 is 18. That's the total mass number. But the mass number, is it the same as the mass? No. The mass number tells us how many protons and how many neutrons we have. And so in this water molecule, I have a total of 18 protons and neutrons in some combination. If I want the actual mass of this, then I need to know how much each of these atoms weighs. And so the H1, I see that to 10 decimal places. So I have two of those. It's going to be 1.0078250321 U. Okay, and then I have an oxygen 16. An oxygen 16 weighs how much? 15.994914622 U. And then add this together. So two hydrogens, one oxygen, these are the masses of those. And so when I add these together, I got 2 times 1.00782 50321 1. Hey, can you check your calculator? Can you try to input that number? 1.00782 50321. Were you able to input that entire number? Yeah? Including the 1 at the end? What kind of calculator do you have? Oh, is that a programmable calculator?
Yeah.
Oh, unfortunately, you're not allowed programmable calculators. You have to use a non-programmable calculator. With a programmable calculator, we don't have this issue. With the non-programmable calculators, we have this issue. And this is what the issue I want to talk about right now, just briefly. And so if you have a standard calculator that's allowed on like SAT, ACT, GRE, MCAT, those types of exams, then one thing you'll notice is that you're going to be limited to how many sig figs you can have. And what's the maximum? The maximum is 11 sig figs. If you have more than 11, what's going to happen? Or 10. The maximum is 10, sorry. It's 10 digit. The maximum is 10 digits, or 10 sig figs would be the max. What happens if you have 11? Yeah, you can't input it. You got to round it off. And so what happens with the calculator is, when you do calculations with a standard calculator, it only carries 10 digits. Any other digits beyond 10 are automatically rounded by the calculator. And so the calculator causes round-off error just in its normal operations. And so if you did the calculation on a standard 10-digit calculator versus a programmable calculator, you might get a slightly different answer due to rounding or round-off error. And so one way to minimize round-off error is this. I know it's an annoying feature. I recommend the Casio FX115 ES Plus, but some students might be complaining to me right now saying, man, all the answers are in fractions, and then you have to hit the SD key to convert it into decimal. Have you run into that problem? It's very annoying. I don't like it too. But the thing is, if it's in fraction, is there any round-off error? There's no round-off error, and so you're going to get a better answer, a more accurate answer. if it's left in that form. Does that make sense? And so if we represent the decimal as a fraction, we don't have the round off issue. All the digits are going to carry. But when I do this, okay, 2 times this equals plus this bottom number, 15.994914622. And my calculator won't take that last one. And then when I write this, this comes out to 18.0105646. How many decimal places am I allowed? I'm allowed 10 decimal places. How many decimal places did I get from my calculator? 2, 4, 6, 8. I only got 8 decimal places. And it was rounded after that. And so I can't add 0, 0 here because I don't know what it was before they rounded it. And so I'm stuck with this here. And so I can only go 8 decimal places even though I'm allowed 10 because my calculator is limiting the sig figs in my answer, not the question itself. All right, so I'm stuck here. This is why there's only 8 decimal places here. But this water molecule weighs that. That's a lot. And so, you know what? The mass number and the mass are actually kind of close, right? Do you see it? The mass number is 18. Why is that? Why is the mass number and the actual mass kind of close? Because the mass number is the protons and neutrons, and so what's missing? Electrons. Electrons, do they weigh much? No, so they are going to be close. So this is going to weigh about 18 U, we'll say. But what are the other water molecules that you had today? The other water molecules that you had today was an H1, O16, and then a little heavier hydrogen, H2. Now this little bit heavier hydrogen has the same number of protons, so we call it hydrogen. It's element number 1. And it will have the same chemical properties, it's just a little bit heavier. That's the only difference. And so the only difference between these two is this one weighs a little bit more. About how much does this one weigh? Well, the total mass number is 19. 1 plus 16, 17 plus 2 is 19. And so this is going to weigh about 19 U. If I wanted to get an accurate mass for this, then I'd have to use this table. What's this table called? This table is called the table of isotopes. And you can find this table is not comprehensive. Where can you find a more comprehensive table? In a reference book, such as we have a couple of reference books. One is the Merck Index. The Merck Index is a very common reference book that's been used. This is pre-Wikipedia days. But you can find a lot of data. And the data that's found in the Merck Index is primarily drugs and biological molecules. Merck Index is a drug company, but this book is not just for their drugs. This book is just a general reference for chemists and biologists, biochemists. A better reference for physics, math, and chemistry is called the, did I tell you about this? The CRC handbook? Which is on the 99th edition now. This is a better reference book. In here you'll have a huge table of isotopes in which you can find pretty much all of them. Not only that, you find a whole bunch of other data for physics, math, chemistry. So this is a really good book. It's expensive, $185.01. It's $185.01 for the latest edition, but if you go down to the 2007 edition, 2012 edition, they're only asking $49.99. The data's old, but hasn't changed that much. $11 used. Price goes way down. 750. And this is a really useful book. It's a handy book to have, and it's worth buying. Thanks. You continue on in science. All right, so anyway, let's continue with our water here. So you drank a little bit heavier water, right? You can't taste the difference though, but you know, physically it'd be a little different. Chemically, it's the same. Okay. Any other water molecules you consume today? Yeah. You consume this one, H2O16H2. H2O16H2 should weigh roughly what? 20U. Wait a minute. Actually, I missed one. The one I missed is this. H2O16H1. These are the two combinations. This would weigh 19, about 19U. Do you see that these two are the same? If they're the same, then why did I write it twice? This, you know, all I have to do is flip this molecule around 180. That's it, and then I get the same thing. Why I wrote it twice is because of statistics. Now, when you look at this, these are distinct statistically because the first atom is H1 or H2. We have a choice. And the second atom can be H2 or H1. We have a choice. And then for both these choices, we get this combination. So when we look at the statistics of this, we have to factor that in. But for us, for right now, not going to worry about it. Okay, is that it? Is that all you can think of? Can you think of any other water molecules that you consume today? Yeah, with oxygen 17. So H1O17, H1. How much does that weigh about? 19U. And then H1O17, what? H2. This one's going to weigh about 20U. And then H2O17, H1, which is the same. You see that these are the same. This is going to weigh 20U. We just count it because of statistics, but we're not getting into the statistics of this. Then we have H2O17, H2. This one would weigh how much? About 21U. If you wanted the more accurate mass, then we'd have to figure it out because O17 weighs 16.99913,150. Figure it out. Is that it? Are there any other water molecules? Yeah, oxygen 18. So we're going to have H1O18, H1. H1O18, H2. H2O18, H1. And H2O18, H2. The first one weighs about how much? 20. The second one, actually both of these are the same, are going to weigh about 21U. And then finally, this one's going to weigh 22U, about. And so the lightest water molecule you consume today, H1O16, H1 at about 16U. The heaviest water molecule you consume today is H2O18, H2. You couldn't taste the difference because they're going to taste the same. Probably couldn't feel the difference because there's so many water molecules in a glass of water. And so, a lot. How many different water molecules did you drink? They're only different in terms of mass. But how many different water molecules did you drink? The mass being the neutrons. if we look at the mass number, 18 protons and neutrons, add an extra neutron here, etc. We could do the mass number. But how many different ones? There's one. Okay, these two are the same, so we'll count that as 2. 1, 2, 3, for a total of 9. And so in this sample, we have 9 different water molecules. Chemically, they're the same, but they just weigh different amounts. The lightest one was 16U. The heaviest one, 22U. Now, what is the average? Well, if the lightest one is 18, the heaviest one is 22, what is the average water molecule? You know, how heavy is the average water molecule? The average, well, what's the average of the 18 and 22? The average. Like, let's say the heaviest watermelon at the store was 22 pounds. The lightest was 18 pounds. What's the average weight of the watermelon? Is 20 pounds, right? And so the average mass of the water molecule that you consume should be 20U. That's the average, but it turns out the average is not that. It turns out that the average water molecule weighs 18.02U. Now, I could be more precise here. There are a lot more digits, so I'm not going to carry them. I'll just do this to 4 sig figs. 2 4 sig figs. All right, when I think about how can the average be 18? You know, I consumed water molecules from 18 to 22U. How can the average be 18?
More exist that are 18.
I'm sorry?
More exist that are 18.
Yeah, exactly. That's the reason. The reason is because 99.9% of the water molecules you drank were H1O16H1. And therefore, we have something called a weighted average. A weighted average is going to be heavily weighted towards this because this is the most abundant, we call it, water molecule. All right. So that brings us to 2 levels of chemistry. If we're looking at it at the particulate level, then this is the way we visualize water. If we look at it at the macroscopic level, if you have a cup of water, do you really care about the individual water molecules? Not really. You just care about the average water molecule. So if we have a cup of water that's macroscopic, and so for macroscopic, we use the average. For particulate, we look at each water molecule individually because the situation is this. The average is 18.02, but will I ever drink a water molecule that weighs 18.02? And the answer is no. There's no water molecule that exists that's 18.02, that's just the average. And so if I'm at the particulate level, I'm looking for a water molecule that weighs 18.02, I'm never going to find it. That's the average. And so it depends. Are we working at the particulate level or are we working at the macroscopic level? At the macroscopic level, we just look at averages. In this class, what do you think we look at mainly? At the particulate or at the macroscopic? At the macroscopic. And so we aren't going to be looking necessarily at individual. We're just going to be looking at the average. And so this brings up 2 masses when we're looking at atoms. When we look at atoms, the same thing happened. Let's take a look at hydrogen. And this is going to be a weighted average. Because if it wasn't a weighted average, what's the average between 1 and 2? Let's say, what's the average? If one hydrogen weighs 1, the other hydrogen weighs 2, the average hydrogen should weigh 1.5 halfway between. That would be if it's a 50-50 or 1-to-1 mixture, but it's not. If you look at this mixture, it's mostly H1. And since it's mostly H1, the average should be much closer to 1. Do you know what the average hydrogen weighs? The average hydrogen weighs 1.00794 U. That's hydrogen, 1.00794 U. Now, are you going to find an atom of hydrogen that weighs 1.00794 U in nature? Does the hydrogen atom exist that weighs that? No, it doesn't exist. That's the wrong periodic table. Actually, this is to only 4 decimal places, but it's the same thing. And so we see 2 numbers in the periodic table. The first number is Z, number of protons, which defines the element, or it's the element number. Hydrogen's element number 1 proton. The second number we see in the periodic table is the average mass of a hydrogen atom. And so this is called the atomic mass. You say the average atomic mass, which is just called the atomic mass. Okay, now if we're working at the particulate level, if we're looking at individual atoms, then I'm never going to find an atom that weighs that much. The individual hydrogen atoms are going to either weigh this or this. What does the average oxygen weigh? Well, again, it's a weighted average. It's a weighted average, and it's going to be weighted toward the most abundant species. What's the most abundant oxygen species? Oxygen 16, 17, or 18? 16. In fact, look at it. It's 99.8% oxygen 16, which means the average should be very close to 16. And so let's see what the average mass of the oxygen is. And so we could just go to the periodic table for that. Take a look at the average here. And the average is 15.9994. So oxygen is 15.9994 U. And so we have, in water, we have 2 hydrogens, 1 oxygen. And so if I take 2 average hydrogens plus 1 average oxygen, what am I going to get? And so let's go ahead and do that. 2 average hydrogens would be 2 times 1.00794 equals plus 1 average oxygen, 15.99, oops, I screwed that up. 15.9994. I screwed that up again. 15.9994 plus 2 times 1. Does somebody have it? I miskeyed it, so let me do it again. 2 times 1.00794 equals plus 15.999994. 18.015. 18.015. How many decimal places am I allowed? 4. So 18.0152. And so this is where I got the average. The average I just said is 18.02. I just rounded it to 462. So the average was. But we aren't going to find an average water molecule. We're just going to find individual water molecules that we had averaged. The same thing like lithium, you know. Are you going to find any lithium atoms that weigh 6.941 in nature? No, because that's the average. Are you going to find any beryllium atoms that weigh 9.01218 in nature? No, because it's the. All right, that was a trick question. I baited you on this one because are you going to find? Yes, you are going to find beryllium atoms that weigh this amount. Why?
There's only one.
Because there's only one isotope of beryllium. How did I know that? I didn't know that. I just saw that on the table, and got lucky I remembered it because I could have been thrown off. In fact, all beryllium, all 100% of all the beryllium atoms in nature are 9.012. All, and so Dalton would have been correct. Dalton would have been correct if we were only looking at beryllium because all beryllium atoms are identical. They all weigh the same. They all have the same atoms. Are there any other ones that would have thrown me off? Fluorine. All fluorine atoms. All 100% weigh this. Are there any other ones? Yeah, there are. There are multiple other ones. But the most important ones are fluorine and, yeah, fluoride would be part of it. Fluorine and phosphorus. So fluorine and phosphorus are two to remember. Those don't have multiple isotopes. All the others have multiple, so all the others would have an average that doesn't equal any of them. And beryllium, yes, but beryllium's so toxic, nobody uses it. So we don't have to worry about beryllium. But phosphorus and fluorine people use. I mean, people brush their teeth. I thought I turned off my room. Sorry. Yeah, people brush their teeth, and then to power your bodies, you need ATP. Have you heard of ATP, ADP? Yeah, that's phosphorus. So those are two important ones. Some people don't use fluoride. That's fine. All right, now that brings up the question, this is the average. So how can we tell if an atomic mass is the average or if the atomic mass is the mass of an individual atom of a specific isotope? And so that's going to come here. So when we look at it, like for example, H1 is 1.0078250.321 U. This we call atomic mass. It's the mass of an atom, so it's atomic mass. But we don't use atomic mass for this one, because that might get confused with this one. Over here we use the term atomic mass. And we don't use average atomic mass, we just use atomic mass. So if that one's called atomic mass, then we better call this one something else. This one, what we're going to call, actually both are atomic masses, this one we're going to call isotopic mass. Okay, so isotopic mass refers to the mass of a specific isotope. Atomic mass just refers to the mass of the average of all the isotopes. So how do we calculate a weighted average? How we calculate a weighted average is like so. We'll need the data. And let's go ahead and go through a couple of examples of calculating the atomic mass or the average atomic mass. And so the average atomic mass, again, average is left off, so people just call this atomic mass. To calculate the atomic mass of it, we need the either the fractional or decimal abundance. Okay, the decimal abundance is just a percentage. Now, those percentages, where did those come from? Do you know where the percentages came from? How do they know 99.9% of hydrogen is hydrogen 1? How do they know? How they know is by these peaks. These peaks are 100% of all the neon. So number one, from the mass spectrometer, we know that there are 3 isotopes that occur. And based on the 3 isotopes, we can see by the size of the peak. If we add these 3 peaks together, that's 100% of all neon. And so out of that 100% of all neon, what percentage is 20? What percentage is 21? And what percentage is 22? And so from these peaks, we can get the natural abundances or the relative abundances of each atom from these peaks. Now, these vary a little bit. So for example, if we look at a sample of water, you know, there's some heavier water molecules and some lighter water molecules. And so if we go deep under the ocean, do you think deep under the ocean we're going to have the same distribution? No. Actually, deep under the ocean, we expect to find more of the lighter water molecules or more of the heavier water molecules? The heavier. And so the distribution deep under the ocean is going to be slightly different than the distribution at sea level, which is going to be slightly different than the distribution at high altitude. So for example, ozone. Ozone, it's easy to tell the difference between ozone that's produced by pollution versus ozone that's in the ozone layer. The ozone that's in the ozone layer is richer in oxygen 16 or richer in oxygen 18? Richer in oxygen 16. The ozone at sea level is richer in oxygen 18. They're both still richer in 16, so I guess I should say a little less rich in 16. But what you do is you get a whole bunch of samples and then you average it, and those are the percentages we see in the table, you know, the averages. And so some places you'll see deviations from the average, higher or lower, but we're just going to take them. And how do we get the averages? I mean, the percentages, we get it from the mass spectrum here. So we'll need that data here, and we'll need to know how much it weighs. Well, if we calibrate this, and we're using a high precision instrument, we could get this to a lot of decimal places, to 10 decimal places for the most expensive mass spectrometers. There, crap. Or maybe they got it more. And so let's take a look at this example. The natural distribution of the isotopes of boron is 19.9%, boron 10. And so here, the fractional or decimal abundance of this would be 19.9 out of 100, or 0.199. Okay, then we'll do the fractional or decimal abundance of isotope 1. And then we'll do the mass, times the mass of isotope 1. Okay, this is the first term, and then this will repeat it. This will be for isotope 2, and it depends on how many isotopes we have, plus isotope 3. In other words, we're just going to take the sum of these. And so let's go ahead and calculate it. Since there's multiplication and division, we do those separately. Should we do the multiplication first, or the, not division, multiplication and addition? Should we do the multiplication first, or the addition first? We're going to do the multiplication first. Multiplication has a different set of sig fig rules than addition, and so we should do those separately. And so that's what they do here. I like to take I like to do it this way. I like to take the fractional abundance. So 19.9 out of 100 atoms are going to weigh this amount, 10.0129370. Okay. And it comes out to 1.99 U. Okay, then we do the other one. 80.1 out of 100 boron atoms are going to weigh 11.0093055 U. And then there's no third isotope. There's only 2 isotopes in this case. How do we know? Because that's what was observed. And then we add them together. If we add them together, how many sig figs am I allowed in my final answer? Because the next step is to sum it. How many sig figs am I allowed in my final answer? Sum it per time.
Yeah. 4.
4? 4 is right. 4 is how many I'm allowed. How did you come up with that?
Because when you add them, you count decimal places, but then when you add 8, when you add them, you get 10.
Yes,
So-
right. Yeah. So this is a little bit of a trick question. A lot of people will say 3 sig figs, but that's wrong. We're allowed 4 sig figs. We're allowed 4 sig figs because it's not the decimal places. When you're doing addition or subtraction, it's not the sig figs. It is the decimal places. I have that right. So it's not the sig figs, it's the decimal. 3 sig figs gives me 4 sig figs. Why? Because 2 decimal places gives me 2 decimal places. And so the correct answer is 10.81. They rounded it. I'd like to see what digit they rounded off. And so I'm actually going to do this calculation really quick, and then we'll take a break. But I'll just do 19.9 divided by 100 times 10.012937 equals that, plus the second term, 11.009355, 10.81. And so I get 10.811. 10.811 U, and then round it to 10.81 U. Okay, then we can do the same thing for lithium, but just looking at it, where do you expect the average around? We'll do a ballpark. If we do this ballpark, then let's just say about 10% is at 6, and about 90% is at 7. So if 10% of them are 6 or weigh 6, and 90% weigh 7, where's the average? It's closer to 7, and it's going to be 6.9. 6.9. It's 90% of the way to 7. So 90% of the way to 7 would be 6.9. It's actually a little bit more than 90% of the way to 7, and so it's going to be a little bit farther, 6.94. Okay, this is not exactly 6, that's not exactly 7, but it's pretty close. All right, what if you, let me just finish with this and then we'll take a break. What if you have more isotopes, like sulfur? How many isotopes does sulfur have? 4. But the most abundant one is sulfur 32, so the mass should be closest to 32. The average should be closest to 32. And so we do this, and the average comes out to 32.065. All right, well, let's stop here. We're going to take a break, and then we'll take a look at this.